Hi, this is Tej Arora. I'm an AWS Certified Solutions Architect Associate. In this video, I will review and summarize the AWS Architectural Best Practices paper. Let me first show you which paper I'm talking about. If you search for it using the query AWS Best Practices paper, it's right here, the first result. Now, you can think of this as version 1 of the architectural guidance from AWS. Version 2 is now called the AWS Well-Architected Framework. Version 1 has some general design principles and some specific design patterns. Version 2 has restructured this information with general design principles becoming pillars of a framework and specific design patterns covered in specific pillars. Version 2 has also added a checklist of questions that drive good practices and behaviors. So is version 1 still useful? I believe so. When I was preparing for the Solutions Architect certification exam, I found this paper really useful. There's a lot of good learnings in this paper for designers and architects. In addition, version 1 is one document of about 50 pages, and version 2, the well-architected framework, is about 6 documents and around 300 pages. In this document, you can learn a lot in very little time. In any case, I will also be posting videos in the future on version 2, the well-architected frame. This particular paper is also very useful for the certification exam, but needs a lot more time studying it. So let's dive right in and discuss this particular paper, the version 1 paper. Before I discuss the contents of the paper, let me share something with you. I have a short video discussing an AWS architecture template, which is a good framework for discussing cloud architecture. You may want to view it before going over this paper. The link is in the description below. This paper has two main sections. The first section establishes why the cloud is a much better value proposition for running your applications compared to traditional models of running applications on premises or in your own data centers. The second section discusses design guidelines, best practices, and design patterns when you are building on the cloud. So let's start by looking at why the cloud is better. The first reason is that on the cloud, you can provision resources as and when needed and almost instantly. To run any application, you need to have basic infrastructure resources like compute, storage, network. And in the traditional model, you have to procure all of these much in advance of running the application. You have to know how much to procure, what configurations to procure. And after you do that, you have to set them all up, install them, configure them, and then wire all the resources. The planning that goes into what to get and how much to get can't be exact, and it relies on fuzzy information because until the application runs and there is real traffic, it's very difficult to predict how much of these resources will be needed. So what ends up happening is either too many resources are procured or too few resources, both of which lead to problems. The other big benefit of using the cloud is that since you can get resources instantly, you can actually run experiments to follow on ideas and innovation. For example, if you are an e-commerce application and you want to try out an entirely new ERP platform, you can do that on the cloud by setting up a separate environment with the new ERP platform without interrupting your main platform on which the business is run. So you could say that cloud enables innovation because it makes it easy to experiment on new ideas. And since environments can be toned down as quickly as they are brought up, there are no long-term cost implications to running experiments. You can set up an environment quickly from your experiment and tear it down quickly, and you only pay for the amount of time that you use the resources. The next reason why the cloud is superior is that AWS gives you resources around the world and it's scalable and highly available. So if you want to run your applications globally, because your users are across the globe, you can provide better latency by taking the applications closer to them. The cloud also enables you to meet compliance requirements. Different regions have different laws relating to the storage of data, and with resources around the globe, cloud makes it easy for you to meet those requirements. The next reason is that the cloud provides a lot of high-level, fully managed services. Fully managed means You don't have to install, configure. You don't have to worry about tuning it for scale and availability. You don't have to worry about backup and disaster recovery for the service. All of that is managed by AWS. You just focus on using the service and forget about the complexity of managing. For example, if you want to use Hadoop or Apache Spark for big data, it's available as a service, and with just a few clicks, you can start using these services. So what this helps you do is you can build new applications faster because you don't have to worry about the extra operational complexity and the development effort needed to use these high-level platforms. You also have access to a lot of new platforms that can propel your innovation efforts. Now you can easily use complex services to handle big data and leverage AI and machine learning algorithms easily. The next reason why the cloud is more valuable is that security becomes a lot easier for cloud applications. Security of the data center and the physical compute and network hardware comes for free. To secure the compute and network layers in your architecture, it's as simple as writing declarative statements. What this means is that security is now part of your design and it can be easily incorporated in your testing. Besides, there are a lot of tools available that enable you to look for security exposure in real time and also act on it in real time. There are higher level security services available to you. For example, you can block denial of service attacks at the edge. You just have to enable and configure this capability. Also note that AWS has spent thousands of engineering hours focusing on security and making it easy to secure the infrastructure as well as the applications on the cloud. Such investment in security thinking is not affordable for each individual enterprise. The investment by AWS into security is amortized across the thousands and thousands of customers that use the cloud platform, and therefore it's a win for all. The next reason why cloud is better is that it enables you to architect applications with cost in mind and with cost controls in your hand. As an architect, you can decide what resources and what configurations are appropriate for your application and choose just what's needed. So cost consciousness should be a part of design and architecture on the cloud. In other words, it is a design tenet on cloud, and there are several features on AWS that enable cost management. You have detailed usage and billing reports available. You can set budgets and alerts if you exceed those budgets, and there's more. And finally, operations on cloud are highly evolved. AWS has invested a lot of time and money on building solid world-class data centers as well as operations around them. There's a lot of tools available for monitoring and alarming, for auto-scaling, and also to make your processes repeatable. You can write your infrastructure as code and automate the setup and teardown of entire environments. This is incredibly useful for operations as it increases automation. The operational maturity on the AWS cloud is useful in all the scenarios. A, if you're just lifting and shifting your application to AWS. B, if you're just refactoring it or rewriting parts of it. Or C, if you're completely re-architecting your application. For example, if you're simply lifting and shifting your application from your data center to AWS, you can start to automate the setup of your entire environment by coding it as a template in the CloudFormation service. So let's just summarize why the cloud is better value for building and running applications. Resources are provisioned instantly and on demand, and you only pay for what you provision. There is no fixed overutilized capacity or underutilized capacity that you have to worry about. All the services are available globally wherever you need them based on your requirements, based on your end users. There's a lot of higher level platforms available that you can start using at the click of a few buttons and without the heavy lifting that goes on behind the scene. Security, which is absolutely crucial, is built in for the data center, and there are tools to make it easy for you to incorporate security into your design and in your code and in your testing. Cost is something that you have a control over when you design on the cloud. And finally, you get access to world-class operations. One thing to realize is that building and running applications in the cloud is a paradigm shift. It's not simply a matter of using different technologies and platforms. Cloud changes the way a company plans, develops, tests, secures, and operates applications. Let's move on to the second part of the paper, which is about design principles on the cloud. This section is a mixed bag of core architectural principles that I talked about in a different video and some specific design patterns. Let's quickly go over each of these sections at a high level, and then we can get into details of each of these. Scalability is core and should be a goal for any architecture, whether it's on the cloud or not. Disposable resources is a general guideline, something designers should remember about the cloud. The idea here is to treat resources as short-lived or ephemeral. Automation is a core trait of any architecture. Loose coupling is a design pattern. It's sort of hinting towards a microservices architecture. Next is about focusing more on services you need and moving away from having to manage servers. This is hinting towards serverless architecture. Serverless is a new design paradigm. The database section is actually a few specific design patterns relating to how you choose the kind of database to be used depending on requirements of your application. Managing increasing volumes of data is just a fact in the modern era. To me, this is more like a subdivision of scalability because any data handling in your application must scale. The section on removing single points of failure could be more generalized as a section on high availability, which is a core architectural attribute. Cost optimization is another core attribute specifically for cloud application, because only in the cloud world does a designer have cost controls to play with. This section discusses caching. I think it should have been more generalized into a section on performance, because caching is just one way to get better performance. And of course, performance is also a core architectural attribute. And finally, security, which is another core trait of any architecture, whether it's on the cloud or not. Now we can dig deeper into each of these sections. Let's look at scalability. Applications need to be able to scale as users grow, traffic grows, and data grows. There's two forms of scaling: vertical scaling and horizontal scaling. In vertical scaling, you just make the resources bigger and bigger as your users and traffic and data increase. In horizontal scaling, we use a number of small resources, and as your load and traffic and data grows, you just use more of these small resources. Overall, vertical scaling has a limit, whereas horizontal scaling can go much further. And horizontal scaling is also generally cheaper because bigger resources can get more expensive as their cost increases non-linearly. Horizontal scaling can be seen in two contexts. The most common scenario, which is a client-server model, and the other scenario, which is batch processing or offline data processing. In either case, the fundamental way to scale is to distribute the load to the application. In the client-server scenario, there are three situations you could have: a stateless app and stateless components, or a stateful app and stateless components, or a stateful app and stateful components. Stateless simply means that when a request is processed, there is no need for knowledge about prior requests. The advantage of stateless is that you can easily scale the components up or down without impacting the functionality of the application. In the full stateless scenario, an application could pull requests to be processed from a queue, or requests could be pushed to it from a load balancing layer or by a DNS round robin method. There is no state information stored about prior requests. Example is an order processing application. In the case where there is some state information about prior requests, in cookies for example, the request serving component could still be stateless, and the cookie could be used as a key to state information kept in a database. Example of this model is an e-commerce application. The case where we have the app and the components being stateful is, for example, databases and gaming servers. In order to provide real-time responses, gaming services need to store user information locally on the server, and users typically have a persistent connection with a specific gaming server. And the way the users are distributed across multiple servers is through a concept called sticky sessions, which is a feature of load balancers, and this feature is used to route a specific user to the server. In the case of batch and offline data processing scenario, the distribution of load is handled by the use of massively parallel architectures. Examples are analytics frameworks such as Hadoop and Spark. Now let's look at the design guideline of looking at resources as disposable. It's important to avoid servers that are long-lived, and the reason is that when there are fixed servers, over time, bad practices gradually begin to pile up. For example, hard coding begins to happen in scripts, configurations become ad hoc, and generally assumptions begin to creep in. This can be eliminated entirely by not using long-term resources and by recreating them as needed. And note that there are enough mechanisms to create new resources easily. One thing to keep in mind is that when you need to change configuration on an instance, it's better to just recreate a new instance with the new configuration. This is the concept of using immutable resources. There are a lot of ways to make sure that when you add new resources, the process is automated and repeatable. And some of these supporting mechanisms include the use of bootstrapping scripts when you create a new VM, and the use of golden images such as AMIs for EC2 instances and EBS snapshots. You can also use golden images for database instances by taking snapshots. Another great mechanism to create resources in a repeatable and automated manner is containers. The additional benefit with containers is that container images are portable across multiple platforms, and the same container image can be used across environments from dev, test to production. Between bootstrap scripts and golden images, typically a hybrid approach is used. For example, for a web service, the web server software can be part of the golden image, but the configuration of the specific web server instance as it comes up can be done via bootstrapping scripts. The Elastic Beanstalk service follows the hybrid model. One thing to keep in mind is that with automated creation of resources, it's not just individual resource instances that can be automated, but entire environments can be automated via cloud formation. Now let's look at the section on automation. Automation is really important, and it's a core attribute of any architecture. What automation does is to remove the human intervention, which tends to introduce errors, and it also allows systems to recover automatically and makes them resilient. Automation also increases agility as it does not require manual intervention. Every layer in the architecture has to be examined for opportunities to automate. For example, the entire deployment pipeline, including building, testing, and deploying, can be automated. The creation of infrastructure can be automated through mechanisms such as Elastic Beanstalk, automatically recovering EC2 instances that have any issues, using Systems Manager to apply changes to a large fleet of systems, and the auto-scaling mechanism that can be used to scale your capacity up and down. There are several tools available to help automate different processes. CloudWatch alarms and CloudWatch events are very central to the entire automation process. Security can be automated through web application firewalls, which is a highly customizable mechanism. One can write rules to block specific request patterns. Security can also be automated through declarative constructs for security groups, routing rules, and network access control lists. Now let's look at the next chapter, which is on loose coupling. This is a general design guideline. It's not a must-have, but it's a nice to have in several scenarios, specifically in microservices architectures. What loose coupling does is it avoids failure in one microservice from cascading to the rest of the services. It allows each service to be developed and released independently. In summary, it provides a lot of flexibility. Another way to avoid cascading of failures from one component to another is for each component to have resiliency in the face of failures of other components. So if we could have mechanisms such as retrying failed requests, caching content. If the server that's supposed to return the content is down or unavailable, it would be very helpful. There are two patterns for loose coupling. One is that there is an API interface for a component, and the other is that the service is discoverable by the clients. API Gateway provides the ability to define and create API-based services, and the service discovery can be implemented via well-known DNS names for the service, or we are looking up a registry of some sort. The other pattern of loose coupling is asynchronous integration, which can happen through, for example, an intermediate queue. Asynchronous integration can also be achieved through event-based processing. For example, a Lambda function can be triggered on an event. Let's move on to the design guideline about using services and not focusing on servers. There's two ways to go about that. One is to use managed services, and the other is to go for a serverless architecture. There are a lot of high-level managed services provided by AWS that can be used without worrying about the operational complexity behind managing them. For example, managed relational database services, Apache Spark, Hadoop, and so on. There is a lot of support on the AWS cloud for enabling serverless architectures. Lambda functions is quite central to that. If you want to build a web application without having to manage servers, you just have to set up the API gateway, Lambda functions, S3 storage, and a database. Using any of these services, you don't have any servers you need to manage. There are many other examples of how you can get a lot of work done without managing servers of your own, such as Amazon Cognito. It enables mobile apps, IoT. It provides fully managed device gateway, Lambda at edge, where you can do processing at edge locations, and Athena is a serverless way to query S3 data. Now let's look at the database section. First thing to note is that on the AWS cloud, it's possible to get enterprise class databases at a very low cost. This section on databases talks about the different kinds of database technologies available and how you can decide which of them to use for your application. Let's look at the different types of databases. Relational databases have a fixed relational schema and are suitable for transactional applications because they support ACID properties on transactions. NoSQL databases have relaxed schema requirements and have a relaxed consistency mode. And as a trade-off, these databases typically are highly scalable and have very low latency and are suitable for a wide variety of applications. Data warehouses are suitable for multi-dimensional analysis of business data, such as retail sales, so that online analytical processing is best done on data warehouses. Search databases provide easy and powerful queries on large amounts of unstructured data, and graph databases are right for applications where the basic data model is a graph, such as social media applications or maps related applications. Now let's look at the workload requirements that will decide which of these database technologies to use. Note that the sections marked in orange are the key factors in deciding which type of database to use. So your data model, whether it's fixed, whether it's flexible, whether it's a graph, if you have ACID requirements, then you need a relational database. If you have online analytical processing requirements, then you need a data warehouse. If what you need is a distributed, highly scalable hash table, such as a key value database, then you need to know SQL databases. Once you've decided which type of database technology to use, the remaining aspects of your workload, which is read-write ratio, data amount, access latency requirements, and licensing costs. These help you determine which database to use within the category. Let's look at read-write ratio. If your app is read-heavy, then you need to scale read requests by using databases that support read replicas. Almost all databases do. If your app is write-heavy, you need to scale writes. This typically needs a multi-master sort of situation, and not all databases support. If you look at the amount of data, the access latency, and licensing costs, all these should help you decide which particular database to use. Note that all these different database types are supported on AWS as fully managed services, and they all support high availability across availability zones or regions, and they're all highly scalable. On to the next chapter, managing increasing volumes of data. AWS provides a lot of scalable services to process large amounts of data. A popular trend is to gather all the data from all your sources into a data lake that can be accessed by various teams in your company using the tools of their choice. High availability is a core architectural attribute, and removing single points of failure is crucial to meeting the high availability goal. You must always expect failures and build resiliency against them. The failures can be in infrastructure such as disks and network links, VMs, etc. They could be region failures, availability zone failures, or they could be in your application. Most of the infrastructure failures are automatically handled by AWS, and your application may not even notice. Regarding application failures, you need to be able to detect them and isolate faults so that they don't cascade further through your application. And you need mechanisms to recover. A good way to recover is to have redundancy in your design and to replace components that have failed. AWS provides mechanisms to automatically create new instances based on health checks or based on increasing load. The data storage mechanisms provided by AWS are quite fault tolerant and scalable. But if you're building your own data storage layer, you need to keep in mind these attributes that help make your design resilient. Have replication in place, make sure there's versioning, just like S3 has. That versioning protects you against accidental or malicious deletion or corruption of data. And make sure you have your solution tolerate the failure of a DC. Optimizing costs is another core architectural requirement. There are many things you can do to optimize costs. First of all, use right-sized resources. For example, you don't use a 16-core VM when a 4-core VM is sufficient for your workload. And use just the right number of instances needed by the load, not more, not less. It's sort of like matching the supply of resources to the demand for resources. Also look at different purchasing options. If you know that you're going to use a resource continuously for a long period of time, you can consider reserving resources which come at a lower cost. If you have ad hoc needs which can tolerate interrupts, then you should consider spot instances. Also look at cost management tools. There's a variety of tools available that help you optimize your costs on a continuous basis. You can look at the usage of resources and the costs associated. Serverless is the ultimate way of paying for compute only when used. When you have your own servers, you're paying for them even when they're idle. Let's move on to caching. Performance is a core architectural requirement. Caching is an important way to meet that goal. So here's some ways you can cache results and improve performance through caching. So if there are results that are obtained by expensive database queries, it's a good idea to cache the results, especially when the results are reusable by multiple requests. For example, if there's a query that fetches the top 50 selling products on an e-commerce site, this would be a great candidate for caching instead of recomputing it for every user. AWS Elasticache is a great tool for application caching. Edge caching is about caching media and other static files closer to where the end users are. You can use Amazon CloudFront for that. Also, be on the lookout for existing services that provide a caching layer on top of other services. One specific example is the DynamoDB accelerator. So in case you're using DynamoDB NoSQL database, the accelerator is a memory cache for your DynamoDB requests, and it improves latency by about 10 times, and it can handle millions of requests. And last but not the least, let's look at security, which is also a very important core architectural requirement. AWS handles security off the cloud. What that means is that it secures the data centers and all the hardware and the virtualization layers beneath the infrastructure. As a customer, you only have to worry about application security and data security. And that is made easy because as a designer, you have controls on security. You can programmatically secure any resource that you create and allow only authorized users, allow only the traffic that is necessary for your application, and encrypt your data for rock-solid security. Some key principles must be followed. Defense in depth. Secure every layer in your architecture. Don't make any assumptions about security of an upstream layer. What if the security of that layer is compromised, either intentionally or due to an error or a misconfiguration? The principle of least privilege. Basically, do not give any more authorizations or any more credentials than absolutely necessary. Real-time auditing is about recording all activity and always being on the lookout for security breaches. Security as code. There are tools that aid in design and management of security. Now, let's look at each of these in detail. Defense in depth. Secure everything, your subnets using network ACLs, your VMs using security groups, and your edge using the web application firewall. Make sure you have well-documented permission policies for users and groups and resources. And make sure you use encryption everywhere. For the principle of least privilege, make sure you follow some good design practices. Use short-term credentials instead of long-term credentials. Avoid users logging into machines unless absolutely necessary. Server should be recreated in an automated manner. Make the servers immutable. And if you have to make config changes just replace with a new server, and use a system manager to make config changes on fleet of servers. Systems manager is hardened to be secure, and the alternative of ad hoc scripts and human logins is insecure. Real-time auditing. It's important to scan access logs and application logs to look for anomalies in abuse. And AWS provides several tools to do analytics on log data, such as Elastic MapReduce, Elasticsearch, and Athena. CloudWatch and CloudTrail enable the logging, both the access and the application. Use Inspector, Trusted Advisor, and Config or other tools to help with monitoring and identifying security issues. And as far as security as code is concerned, you can have reviewed and approved configurations written as templates, and these templates can be managed like application source code. Now you can write templates for things like firewall rules, network access control lists, and OS hardening scripts, and so on. In addition, these templates can be governed centrally for compliance and security by using the AWS Service Catalog. And using that, you can allow access only to approved templates. And because security can be written just like code, it can be easily incorporated into the testing process. And now this brings us to the end of the design principles section. Let's do a quick high-level summary to recap what we have gone through. The paper has two parts. The first part talks about the superiority of the cloud compared to traditional IT. The second part talks about design principles. Why is the cloud better than traditional IT? Well, the assets are provisioned on demand, capacity is available globally, and it's highly available. There are higher level managed services. There's built-in security in the cloud platform. Cloud allows you to architect for cost, making cost a part of design, and the extremely efficient and secure operations on AWS. What are the key design principles? The ones that are marked in orange are fundamental and core attributes of any architecture. The others are sort of design patterns in specific scenarios. So scalability, automation, high availability, cost optimization, performance, and security are core attributes. Disposable resources, loose coupling, using serverless and thinking services, and managing increasing volumes of data are general guidelines. And as for databases, there are some specific design patterns to look at when figuring out your database architecture. This brings us to the end of the video. Thanks for hanging in there. Thanks for watching the video. If you found it useful, please consider clicking on the like and subscribe buttons.